In this tutorial, we're going to practice vector addition. We're going to start with three displacement vectors, delta r1, delta r2, and delta r3, all written in vector notation, meaning that we're using i-hats and j-hats. These are two-dimensional vectors. Let's graph them out first on the xy plane. So we put in our axes. Delta r1 has an x component of 4 meters and a y component of 6 meters, so that means 4 to the right and then 6 up. That's delta r1. We can draw in delta r2, 2 to the right and 7 down, and then delta r3 should be 5 to the left and 3 down. We'll start by adding these vectors graphically, so if we do that, I'll remove their labels. Remember that vectors add head to tail. So we'll leave vector r1 in its current position, move vector r2 up there, move vector r3 over there. Now we've aligned them head to tail, and remember that their sum should point from the unpaired base of the first vector to the unpaired head of the third vector. That means it points down and to the right, something like this. And I'll label that delta r, keeping in mind that delta r is the sum of delta r1 plus delta r2 plus delta r3. One of the best reasons to add vectors graphically is that you can use your drawing to make some very educated guesses about the properties of delta r, namely its magnitude and its direction. So over here in the box on the left-hand side, I'm going to put down some of our expectations for delta r. Just looking at it without making a measurement with a ruler or anything, I would estimate that, assuming each of those boxes is 1 meter wide and 1 meter tall, delta r looks to be between 4 and 5 meters in length, so let's write that down. That's a good estimate for the length of delta r. As for its orientation, vector angles are often described counterclockwise from the positive x-axis, so to get even to the negative y-axis, we would already have to go 270 degrees from the positive x-axis, right? You go 90, you get to positive y, go 180, you get to negative x, 270 gets you to negative y. Well, clearly delta r is a little past that, so just by eye, I would estimate that its angular orientation with respect to the positive x direction, probably something like 280 to 290 degrees counterclockwise from positive x. So we'll write that down, and now we're going to go through and quantitatively check both of these predictions, both the magnitude of delta r and its angular orientation. Alright, so let's do that now. Well, we know that the x component of delta r, which I'll call here delta rx, you could also just call it delta x, they're the same thing, it has to be the sum of all the x components of the three vectors, right? So we literally want to go through and add 4 meters plus 2 meters, and then add a negative 5 meters. So if we add those three numbers together, 4 plus 2 is 6, minus 5 is 1, so that tells us that delta rx is 1 meter. We'll use that in a minute. Now we'll do the same for the y component. So if we want to know delta ry, which again you could just as easily call delta y, it's the displacement in the y direction if these are all displacement vectors, then it's the sum of the three y displacements plus 6 plus a negative 7 plus a negative 3. So if we add those three together, 6 minus 7 minus 3 gives us a negative 4. So delta ry is negative 4. If we want to write out delta r in vector notation, generally speaking, we would write that delta r is delta rx times I hat plus delta ry times j hat. Well, now we know the values of delta rx and delta ry, so let's put in those numerical values here to get that delta r is 1 meter times I hat minus 4 meters times j hat. That's our description of the net displacement vector delta r, which is the sum of delta r1 plus delta r2 plus delta r3, using vector notation. I'm going to write it over here on the left so we can use it again later. Now that doesn't immediately tell us the magnitude of delta r, nor does it tell us the angle of orientation of delta r. Those we need to do a little work to derive from that expression, so let's do that now. Well, the magnitude of delta r you can always remember you get from the Pythagorean theorem, right? So since we have x and y components, that means that the magnitude of delta r will be the square root of delta rx squared plus delta ry squared. Well, we know those two components, they're sitting right there, you can read them off. Delta rx is 1 meter, delta ry is negative 4 meters, but the negative is under the square root. So we'll simplify, it becomes the square root of 17 square meters, which, after you do the math, is 4.123 meters. Rounding off to two significant digits, that means that the magnitude of delta r is 4.1 meters. Well, that matches pretty well with our guess, right? We said it looked to be between 4 and 5 meters in length, so we must have gotten that right. That's a great check to make sure that you didn't botch something under your square root, which of course can happen. Now what about the angle? All right, we'll erase this. Well, remember, graphically, this is the orientation of the three vectors we were adding together, and delta r. If we zoom in on delta r, there are a few ways to figure out this angle. The angle we want is measured counterclockwise from the positive x direction, so it's this angle, going around that way. I'll label that angle theta. We could use that angle and use trigonometry to get it. Personally, I love working with angles between 0 and 90 degrees because then you don't have any ambiguity about the signs. So if we do that, let's label this angle here phi, where I've drawn it so that the sum of theta plus phi equals 360 degrees, right? It makes a circle. So let's note that over here on the left so we can use that later. Well, now we can just do trigonometry in terms of phi, which in my opinion is much easier. So let's get rid of theta for now, keeping in mind its relationship to phi over there on the left. Well, if this is our definition of phi, then we can go through and draw out components for delta r, right? The x component of delta r would be this arrow here, pointing to the right, 1 meter. Delta ry would be pointing down 4 meters. And sure enough, if we added delta rx and delta ry as vectors, we would get out delta r. Well, these two lengths have a very simple relationship with phi, namely that the tangent of phi is the ratio of the opposite length to the adjacent length, so that means that the tangent of phi must be the ratio of the absolute value of delta ry to the absolute value of delta rx. And I put in absolute values because I'm really thinking about ratios of lengths. We don't want to worry about whether things are positive or negative. Clearly, phi is between 0 and 90 degrees the way I've drawn it, so we should put in positive numbers. So if we do that, now we can go through and actually solve for phi, right? So we said that the tangent of phi is the ratio of the absolute values delta ry to delta rx. We know those values. The absolute value of delta ry is just 4 meters. Absolute value of delta rx is 1 meter. So phi must be the inverse tangent of 4.0. And if you do that in degrees, you get out that phi is 76 degrees. Well, we really wanted to know theta, that's the angle counterclockwise from positive x, but we know that theta plus phi is 360 degrees, so it must be true that theta is 360 degrees minus phi. 360 degrees minus 76 degrees is 284 degrees. Well, that matches up well with my prediction that the angle had to be something between 280 and 290 degrees counterclockwise from positive x. Going through these exercises systematically, both graphically and by adding up components, is a great way to double check to make sure that you're actually sensibly thinking about vectors and not making any silly math errors.